So what we have looked at just now is ISP-A advertising its aggregate out through the other ISPs, and then we looked at customer B advertising its network via BGP out through ISP-C, and then which then re-advertises that to ISP-B, and which re-advertises that to ISP-A. What we've also discovered is that every time an eBGP route is re-advertised to its peer, or via an eBGP session, a peering session, it adds the autonomous system number to the path. So ultimately, a router that a router that receives a BGP route has information about all the autonomous systems that traffic will have to go through to reach its destination. And that is part of the information that is used to make the selection of the best path. Okay, let's take this situation now where customer B decides to add another ISP and have a connection with ISP-B. What happens then? Well, in this scenario, customer B will continue to advertise its network to ISP-C as it did before, via its eBGP peer with ISP-C, but it will also advertise its network to ISP-B by its new eBGP peer with ISP-B. So ISP-B receives two advertisements for the same network. It receives one directly from customer B, and it receives another from ISP-C. Okay, so it receives two advertisements for two routes for customer B. One advertised by ISP-C and one advertised by customer B directly. So ISP-B then has to choose the best path to customer B, and it chooses the path with the least number of autonomous systems in the path. So it will choose the route that is advertised directly by customer B, and it will ignore the route that it receives from ISP-C. So the route that it receives from customer B will become the best path. That will become the active route for ISP-B, and ISP-B will advertise only the route that it received from customer B. It will not re-advertise that route that it received from ISP-C. Okay, so it only re-advertises the best path. Okay, so ISP-A receives an advertisement that the 172.31.128.0/20 network is reachable through AS65002, which is ISP-B, and AS65501, which is customer B. So ISP-C does not appear in that path statement that is re-advertised by ISP-B. Everybody good with that? Okay, let's take a look at some of the attributes that we mentioned earlier that can be used to control route selection. We've already mentioned the AS path, okay, which is the autonomous system path. So that is the string of autonomous systems through which the traffic will have to pass to get to its ultimate destination. And as we saw, every time a route is re-advertised, that eBGP router appends the autonomous system number into the path. There are some other things we're going to look at. There's a thing called local preference. Now, this type here, these attributes are kind of classified into different attribute types. So we've got, well, there are 4 different attribute types. So, and the attribute type, so what does that actually do? Well, it's really specify, excuse me, it specifies how that particular attribute has to be treated by a BGP router. So we've got a few here. We've got this well-known mandatory, we've got well-known discretionary, and so on. Let's just go through and take a look at what these attribute types mean. We've got well-known mandatory, must be supported by all BGP implementations, must be included in every BGP update. So, for example, the autonomous system path. Every time the BGP advertises a route, it has to include that information, must include the path. What else is in that mandatory there? Well, we've got origin, we've got next hop. So those 3, path, origin, next hop, must always be included in an advertisement. Okay, now we pretty much know what next hop is. We're going to get into what origin is in a little bit more detail. So every BGP router supports those things. Every BGP route advertisement contains those things. Every BGP update contains those things. So every time a route is re-advertised, it always contains those things. Well-known discretionary must be supported in all BGP implementations, but do not have to be included in every BGP update. So it has to be supported, but it doesn't necessarily have to be advertised. So we have got well-known discretionary, we've got a local preference is one of those things. It's an attribute. And you think, well, what do all the attributes do anyway? They are information that goes into the route selection process. So there is a algorithm that BGP uses to decide what is the best path. And it takes into consideration these attributes when it's making that decision. We've got optional transitive, not required to be supported by all BGP implementations, but if they are, they should be passed along unchanged to other peers. We've got aggregator as one of those. We've got community is also one of those. So we've got these 2 other BGP attributes in the optional transitive category. And then we've got optional non-transitive, not required to be supported by all BGP implementations. If an optional non-transitive attribute is not recognized, it is ignored and not passed to other peers. So we've got these just different attributes which may be passed on, may not be passed on, sometimes must be passed on, depending on the particular kind of a classification, really, of what that type of attribute that is. Okay, so a bit of information there, sort of a bit of an information dump about different attributes. Let's take a look at some of the ones that are more common. So, as we see here, the attributes are used to select the best path so that they feed into the path selection algorithm. Here's some of the common ones. Next hop, local preference, AS path, origin, med, and community. Okay, so we'll get into these and just take a look at what they are, because these are ones that are commonly used, sometimes always used, like next hop, always there. Path is always there, has to be there. Let's take a look at them. So next hop. Next hop attribute is the IP address of the peer advertising the prefixed. So it is the router from which the advertisement was received. That is the next hop. Next hop address must be reachable for the receiving peer to install the route in its local routing table, RIB, routing information base. So it must be reachable. Next hop address must be reachable for the receiving peer to install the route. So we already noted that for IBGP peers, they are not necessarily directly connected. Therefore, the reachability of those peers is achieved via the IGP. Okay, so we'll take a look at that as we go on. Here's another really important point here. The next hop value is changed by default across eBGP peers only, or eBGP links only. What does that mean? That means that with an eBGP peering arrangement, that EGP router receives a route advertisement from another autonomous system. That autonomous system has received that routing information from somewhere else. It re-advertises that route across the eBGP link. When it re-advertises the route, it updates the next hop information in the route so that the receiving router receives that route from its peer, and that peer becomes the next hop. Okay, that receiving router may then re-advertise that route to an IBGP peer within the same autonomous system. When it re-advertises that route, it does not update the next hop. Okay, so bear in mind at this stage, the next hop is a router in a different autonomous system. It re-advertises that route to its IBGP peer, and that IBGP peer receives the route, and the next hop is in fact still the BGP router in the other autonomous system. Now, often the problem might be that that receiving router has no connectivity to that BGP router in the other autonomous system. We'll get into that later on and talk about that in a bit more detail. Okay, so that was an important point. The next hop value is not changed by default across IBGP links, but we can make it change the next hop by using routing policy. Okay, local preference determines the preferred path out of the autonomous system. So here's the scenario. We've got an enterprise which has got multiple BGP peers to different ISPs. By using the local preference attribute, the BGP protocol can influence which path, which particular ISP, in other words, becomes the preferred path for traffic out of that autonomous system. So we can actually say that, well, we're going to have our outbound traffic going to a particular autonomous system, and by using, or going to a particular ISP, and by using the local preference attribute, we can influence which route becomes active. So we'll have the active route being the route to our preferred ISP by using that particular value. So all BGP traffic in an autonomous system flows towards the peer with the highest local preference value. Can be altered through configuration or policy. So we can, when we're actually configuring the peering arrangement, you can put that straight into the configuration. Alternatively, you can create a routing policy which adds the attribute or updates the attribute as the route is exported out of a routing table and advertised into BGP. Okay, so these values are only used within an individual autonomous system. They are not re-advertised across eBGP links. Okay, so that's local preference. Here's an example of that. Here's our two ISPs. On R1, we configure a local preference value of 300, and on R2, we configure a local preference value of 100. With local preference, the highest number wins. So the consequence is that the R1 route will be more preferred over the R2 route. Consequently, the other routers within that autonomous system will install the route towards R1 as the active route, and traffic will be routed via R1 to ISP A. Of course, if you lose connectivity to ISP A, then the other route becomes active. So the scenario here, let's go back and look at that. We've got two different ISPs, two different autonomous systems, and we're using local preference to influence which of those ISPs is used for outbound traffic out of our autonomous system. Okay. AS path attribute used to indicate the path back to the route source and to prevent routing loops. So, two purposes. Routes with the receiving router's AS number in the AS path are considered looped. Okay, so consider a situation where a router, a BGP router within an autonomous system, receives a route advertisement, and in that route advertisement's path is its own autonomous system number. What does that mean? That means that at some point that router or that autonomous system must have advertised the route, and now it's receiving the same route advertisement back again. Okay, so what it does, if it receives that, it completely drops that route. It does not install that route, because that would be a loop. So the example here, so each router on the edge of the AS adds its own number, and so as we can see, the numbers are added as every route is re-advertised. Okay, origin, added by the router that injected a route into BGP and described from where the route information was received. Okay, so as we said earlier, every BGP route is originated from some other protocol outside of BGP. BGP does not by itself learn any routes. All the routes that it knows about were obtained from another protocol, either by policy or by configuration. So there are three possibilities. It either got the route from an IGP, it got it from an EGP, or it doesn't know where it got it from. It got it from somewhere else. Okay, so the IGP, well, that would be relatively common. It would have either got it from a static route, an aggregate route, from OSPF, from ISIS, or some other IGP. Okay, that is probably the usual way. E is actually a redundant, I guess, attribute. There was a long time ago a protocol called EGP. It's no longer used at all, and therefore that particular attribute, the E attribute, is really redundant. Okay, it's not used anymore. And then there's the incomplete. In other words, it doesn't know where it got it from. Now, this is also used as part of the route selection process. Each of them is given a number. So IGP is a 0, EGP is a 1, incomplete is a 2, and the lowest number is the most preferred. Okay, so if we're looking, so when in the part of the route selection process, an origin with a value of 0. So with Juniper routers, it's actually put in as an I. Same goes for Cisco routers. That is the most preferred. The E, next most preferred. The question mark, we don't know, is the next, or the least preferred out of those three. So all this is fed into the algorithm, the best path selection algorithm, and influences what route becomes active, what is the chosen best path. Okay, these are common attributes that you will commonly see in a BGP route. Okay, the MED attribute is used when you have more than one connection to another autonomous system. Let's just say, for whatever reason, I have multiple connections to an ISP. Let's just say that I have different locations. I have a branch office, I have a head office. My branch office has an ISP connection, or has a connection to my ISP, and my head office has a connection to my ISP. But I would like my ISP to send traffic for my organization to my head office rather than to my branch office. How can I control that through BGP? I control that using the MED attribute. So with this attribute, we can put it in configuration, or we can put it in policy. When the route is advertised to my ISP, both from my branch and from my head office, the MED attribute is advertised with those routes. The receiving routers in my ISP look at that MED attribute, and that MED attribute influences which route back to my autonomous system becomes their active route for sending traffic back to me. Okay, so in this case, I would influence it so that they sent traffic to my head office rather than to my branch office. Okay, so I could actually influence how that worked. Okay, so outgoing traffic can happily flow from my head office to my ISP, can happily flow from my branch office to my ISP, but receiving traffic, I may say, well, actually, I want that to come back into my head office because I'm going to be controlling how that is routed internally, and I want it to come in, through that particular peer. So you can control that using the MED attribute. So it's how the other routers, how your peer sends traffic to you, but that those peers have to be part of the same autonomous system. Okay, so the scenario that I mentioned where we've got the same ISP, but in different locations, then we can control how that traffic comes back into our organization, back into our autonomous system. In this case, the lower values are better. Okay, so we're looking at attributes that control the best path selection. So here's the example here. We've got a route with an MED of 20. We've got a route with an MED of 10. and 10 is better than 20. So that is advertised. That is an attribute that is advertised by our BGP speaking routers. And there we are. The traffic comes back from R2 back into our organization. Okay, community. Community attribute, very commonly used attribute. It is a way of tagging routes. It's got nothing to do with what the context or the meaning we normally associate with the word community. Okay, forget about that. It's got nothing to do with living in a little community. Okay, nothing to do with that at all. It's just a way of tagging routes with a number so that we can group routes together. We might say all routes of a particular location or a particular type. We're going to give them a community value. We will then set that community value onto our routes as we export them out. And the purpose of doing that is so that we can then use that community value to influence route selection, our route selection process. We may decide to import routes with a certain community or not import routes with a certain community value. So we can use a community value in the future as a way of treating a group of routes in a particular way based on the community value that that route has. Now, a route can have multiple communities, and we might be identifying a particular value, just one of those community values, and we're saying if the route has this community value, then we're going to treat it in a certain way. Maybe we'll ignore it, maybe we'll import it, whatever it is. So it's a way, it's just an identifier that we get to put on a route so that we can use that to select routes that have some commonality amongst them, some common factor. So routes that are of a particular type have a particular community. Okay, so they were the attributes. Let's look at how the active route gets selected. So once BGP verifies next hop reachability and that no loops exist, it selects the active route as follows. Number one, prefer the highest local preference value. Okay, so local preference is the first thing it looks at. If the local preference value is higher, if one route has a higher local preference value than another, that's the route that becomes active, end of story. Okay? But what if we haven't set the local preference value? What if we're just using the default local preference, which is actually 100, value 100? That's the default. And all the routes have got a local preference value of 100. Well, they're all the same, so we can't make a selection based on that. Okay, the next thing we're going to look at, let's look at the shortest autonomous system path length. So now is the one that has the least autonomous systems in its path. That's the best path. That's the one that's going to become active. Okay, what if they're all the same? The preference value is the same. The shortest path, have all got the same path lengths. Then what happens? Prefer the lowest origin value. So we've got routes that may have been originated from an IGP. They got a value of 0. We've got other routes, we don't know where they came from. They got a value of 3. All right, well, the ones that originated by an IGP, they're going to become active because they've got the lowest origin value. Okay, their value is 0. Okay, so they will then become active. What if they're all originated from an IGP? Okay, so they've all got the same local preference value. They've all got the same number of autonomous systems in their path. They've all come from an IGP. Now what? Prefer the lowest MED value. Okay, so this is where MED is now beginning to influence which path becomes active. What if the MED value is not set? Okay, not using that. Prefer routes learned from an eBGP peer over routes learned from an iBGP peer. Okay, so eBGP routes will become active over iBGP routes if all the attributes from 1 through to 4 are the same. Okay, so this is a route selection process. All right, they're all learned from eBGP peers. Now what? Prefer the best exit from the autonomous system. So it looks inside of its own routing information in the autonomous system and finds the best exit. That's all the same. Then 7, for eBGP received routes, prefer the current active route, otherwise prefer the routes from the peer with the lowest routing router ID. Okay. Getting a bit desperate now. We have to decide somehow. 8, prefer paths with the shortest cluster length, and 9, prefer routes from the peer with the lowest peer ID. Okay, so usually by the time we get down to there, we've made a decision, you know, kind of based on numbers 1, 2, 3, 4, or 5. We've usually made a decision by then. If we haven't, then we go to 6, 7, 8, and 9 and start looking at those things to make a decision on what is going to become the best route. There's a lot of things you can control here. Notice that community didn't get mentioned in there, okay? So community is not part of a route selection process, but what it is usually used as part of a route policy where we decide we either are going to import routes of a certain community or we are not. So it's really, the community is really a filtering mechanism where we're filtering it as part of a policy we're matching on a particular community value. We'll get in and you guys will actually do this, okay? You're going to set this stuff up, you're going to do labs on this, and you're going to see it all working. Okay. All right. Okay, let's look at iBGP versus eBGP. We've already mentioned this. iBGP used within an autonomous system, that's internal BGP, whereas eBGP, external BGP, is used between autonomous systems. Okay, we've already established that. iBGP sessions are usually established between loopback addresses, and we use the IGP to maintain sessions regardless of physical topology. So essentially, the IGP is going to maintain connectivity between our peers, between our iBGP peers. Okay, so just say we're running OSPF. It's OSPF that provides us with reachability information between the peers, which often are not directly connected to each other. eBGP sessions are established using the IP addresses of the physically connected interfaces. Okay, so that's different. So you notice that the iBGP peers are established between loopback interfaces. So we've got the address on the loopback interface being the peering address, the address we set up in the peering arrangement. So we're going from, say, looking at this autonomous system here, we've got R1 loopback interface peering with R3's loopback interface. So the addresses in the peers is loopback to loopback. Of course, that means that our loopback interfaces are going to have to be included in our IGP. Okay, so when we're setting up our IGP and our interfaces on our IGP as to what's included in our IGP, we must include the loopback interface to provide connectivity and reachability between those loopback interfaces so that we can establish those peers. Does that make sense? Okay, we're going to have that.
But you can use in your configuration the addresses of the interfaces for the IPGP, or it has to be the loopback address?
Standard practice is we use loopback interfaces. That is standard practice for IBGP. That is standard practice. The reason for that is because those addresses don't change. So the loopback is always active. Okay, it's possible for a physical interface to go down, to lose connectivity. It's possible, but the loopbacks are always up. Okay, so what you don't want is instability within your peering arrangements. Well, if the router dies, yeah, well then, of course, yes. But what you don't want is any kind of instability within your BGP peering. Okay, you don't want that. So you generally set it up between your loopbacks. If you do happen to lose connectivity between a particular link, then your IGP will reroute that traffic through another way. eBGP, on the other hand, are different. They're established using the IP addresses on physical interfaces. So with our IGP session, it's the physical interface address on each side of that link that becomes our peering addresses. Okay, physical address to physical address. Okay, the IP address of the physical interface. Okay, now to avoid loops, BGP speakers do not propagate IBGP receive routes to other IBGP peers. Okay, what does that mean? Look at this scenario here. We have got 3 BGP speaking routers within this autonomous system. R1 is receiving routes from autonomous system 65502 via its eBGP peer with that autonomous system. So it receives route advertisements. Okay, R1 re-advertises those routes to its IBGP peer, which is R2. However, R2 does not re-advertise its routes to its, or those, it does not re-advertise those IBGP routes to its IBGP peer, which is R3. Okay, so the IBGP routes are not re-advertised. So where you have an IBGP peer, routes received via that peering arrangement are not re-advertised to other IBGP neighbors. Okay, what does that mean? That means if R1 is going to get those routes to R3, or if R3 is going to be able to receive routes from R1, R3 must have a peering arrangement with R1. Okay, so the standard logic then is that you must have a full mesh of peering arrangements between all of your BGP speaking routers. Okay, a full mesh. Now, that can cause some problems with scalability if we have a lot of BGP speaking routers, but there are solutions to that, which we'll take a look at later on. Okay, next hop propagation. This is something we've mentioned earlier on. By default, IBGP peers do not change the next hop for routes received from eBGP peers. So why is that a problem? Why is that a problem? Let's look at this scenario here. We've got R1 here receiving routing information through its eBGP peering arrangement with its autonomous system AS65502. It's receiving routing information. The next hop for that on that routing information will be the physical address or the IP address or the physical interface that it is peering with over there in Autonomous System 65502. In this case, that physical that address, the IP address of that physical interface is 172.24.1.1/30. So that is the next hop address for the routing information that it receives from that autonomous system. That's all fine, as R1 has a connection to that address. It's directly connected to that address across this link. Not a problem for R1. R1 re-advertises that route to R2, and it says, hey, guess what? I've got routes for all these networks, and the next hop for them is 172.24.1.1/30. And R2 says, well, that's great, but I have no idea how to get to 172.24.1.1/30. Why doesn't R2 know how to get to that particular address? Why wouldn't it know? Yeah, so R2 doesn't know how to get to this BGP speaking router over here in AS65502. It doesn't know how to get to 172.24.1.1. Why does it not know how to get there? Exactly. How would it know? Because R2 is running its IGP for its own autonomous system, so it has routes for all the routers in its own autonomous system, including R1 has routes for that. But its IGP is not giving any routing information to that router over there in that other autonomous system. It has no route for that. Okay, and we'll assume we don't have any static routes set up to it. So we'll just assume that we don't, because why would we? And so R2 says, well, that's great, but I have no clue of how to get to that particular router or that particular next hop address. So there's a few ways of overcoming that problem. One of them is to include the external interface on R1 in the IGP. Okay, so the interface that is actually connected to that BGP peer could be included in our IGP as a passive interface. If it is included as a passive interface, then that network, the 172.24.1.0/30 network, will then be advertised by the IGP, and therefore R2 will then know how to get to that particular network via R1. So it will do a recursive lookup in its routing table, find that network, find that the next hop is via R1, and be able to send traffic there. That's one way of doing it. The other way of doing it is to use routing policy and make R1 update the next hop information when it re-advertises the route to R2, and there is a next hop self statement that we can create in a policy to update that next hop information as the route is re-advertised. Remember what routing policy does? It allows us to update attributes as the route is re-advertised out. So it's an export policy. So as we're exporting the route out of our routing, as R1 exports this route out of its routing table, it can update that attribute, the next hop attribute, to say, hey, I am the next hop for this route. And therefore R2 will then send traffic to R1, which will in turn send traffic across to its peer. So there's two ways of solving that problem. Any questions about that? It's just an important. This is standard BGP. It goes Juniper, Cisco, anything, absolutely any device. This is how BGP works. It's not just Juniper. Yeah. So regardless of the platform that you're configuring it on, this is how BGP works. All right. It's not just Juniper. Now of course, we're using Juniper, but this is how BGP works. all right, regardless of your platform. Okay, so there's two ways of solving that problem. Okay. So it's an important thing to recognize that when you advertise a route via iBGP, the next hop attribute is not automatically updated. Okay, so let's look at the default BGP advertisement rules. So iBGP advertisers routes learn from eBGP. So here is our router here in AS5501, re-advertising those routes to its iBGP peer. eBGP advertisers routes learn from iBGP or eBGP. So here it is, that BGP speaking router re-advertising the routes that it has learned from its iBGP peer. iBGP does not advertise any routes learned from iBGP. Okay, so if we have peering arrangements here between our eBGP peer router, and we have iBGP peers with the other two, and if they don't have a peer with each other, then well, you know, if they do appear with each other, they will not re-advertise those routes to each other. I guess that's the point. So we've got a full mesh happening here, but the iBGP routers do not re-advertise routes received via iBGP peers. Okay, so those two IGP speaking routers there will not re-advertise those routes that they receive from their other peer to each other. Okay, so they are the default BGP advertising rules. Now you can change that by routing policy, but that's how it works by default. Alrighty, so we're going to take a look at configuring and monitoring BGP. I noticed that we're getting pretty close to lunchtime there, and we might not have enough time to go through all that prior to lunch. So what we might do is we'll take a lunch break now, and I'm sure you'll got enough information in your head for one morning. We'll take a lunch break, we'll come back after lunch, and then we'll get into configuring and monitoring BGP. See you back at 1.